Hey folks, this is my talk on memory-efficient GPU volume path tracing of AMR data using the dual mesh. This is joint work between the University of Cologne, the University of California in Davis, and people from NVIDIA. Our objective is to render very large AMR datasets. We want to do this on GPUs. We're interested in very high quality rendering with volumetric path tracing, and our prime objective is that interpolation is smooth even at the level boundaries. AMR datasets come in different flavors. The examples here are an octree on the left side, block structured AMR on the other side, and what they differ in is how they refine subgrids. But a commonality of this data is that they are usually cell-centric, which is indicated by those white dots here in the illustrations. And if you want to perform smooth interpolation in the presence of cell-centric data, what you run into is T-junctions. And because of those T-junctions, you cannot just use trilinear interpolation. So the question is how to render these data. And the way that we will consider is the one that very popular visualization systems, such as, for example, Visit, adopt. And what those visualization systems do is they render on the dual grid. And how do we construct the dual grid? Yeah, Visit would take the original data, and then it would take each grid of, say, this octree here, take its cells, and then shift it in the X, Y, and Z direction. And if it shifts to the left or to the right, it's kind of like an arbitrary decision. But you have to stay consistent with that. And you can also already see, if you do this, that there's like this procedure is undefined at the level boundaries. So you shift one row out and you shift one column out, and they don't appear in the dual mesh, and you have to deal with this somehow. And what people do in order to deal with this, they introduce so-called stitching cells. You can see this here in 2D. What I introduced is like general rectangles, and in 3D those are hexahedra, and there are other like generally unstructured elements like three-dimensional unstructured elements such as tetrahedra, pyramids, wedges, and so on. And then you can also see that there are that I introduced a bunch of hexahedra, but these hexahedra they are actually cubes. They're actually voxels. So representing these hexahedra as general hexahedra, like with say 8 integer indices, and with a shared set of vertices, is quite wasteful in regards to memory consumption. And there's obviously a lot of compression opportunity that we are missing out on here. So if you, for example, take those data sets here, some of them are like out there in the wild. You can download them from the internet. Others are from collaborations with our partners. If you take, for example, this molecular cloud data set from the astrophysics group at the University of Cologne here, then you can see that a high percentage of its cells are actually hexahedra. But if you analyze those hexahedra further, you will find that 98% of the hexahedra are voxels. This is quite wasteful. We don't know so much about compression rate yet, but we can already imagine that there's quite a lot of compression opportunity that we're missing out on here. Let's recap a little bit of terminology before we start discussing how we optimize this dual mesh data structure. I will be mentioning cells, and cells have different refinement level, like these are level 0 cells. This is the next coarser level, this is level 1. These are level 2 cells, and then we have grids that the AMR data comes with. These are level 0 grids, level 1 grids, level 2 grids. So if we take this AMR data, what we do is we create the dual mesh with all its stitching cells, be it voxels, be it general hexahedra, general elements, as you can see here. This is the dual mesh of this data. All these here are like tetrahedra or pyramids or whatever. These are general hexahedra, and these we think will be voxels, but we don't know yet. These are the obvious voxels in the data set, so we were able to identify them directly. So the question is now, how do we identify the voxels that are voxels, but that are located at the boundaries? And this is actually pretty simple. These voxels here, as you can see, they have vertices, and the vertices are the cells of the original grid. And if all the vertices of these hexahedra are from the same level, then we know that they are a voxel and not just a general hexahedron. So in that way, we can easily identify all the voxels in the dataset. So this allows us to identify all the voxels, and we now know what the voxels are and what the genuine stitching geometry is, and we can distinguish between the two. So, and then what we propose is to take those voxels and construct gridlets from them. For that, we take this imaginary grid of macro cells and we project the voxels onto that grid. So, and by doing so, we first start out with like this grid is imaginary, and then we just activate cells by projecting the voxels onto that grid. Here, what we have is like 2x2 gridlets, and in reality, what we use is 8x8x8 three-dimensional grids. And whenever we project a single voxel onto one of the macro cells, that macro cell will later become a gridlet. We hope that most of the macro cells will be completely full, like all of their voxels are occupied, but some of them won't. This is not a big problem, because then we'll just have, like this here is a gridlet of size 1x2. And as the hull of that gridlet is still convex, this is fine, not an issue, and then we just store that this is a 1x2 gridlet, and then this is fine. And this is like a 2x1 gridlet. So then we have some gridlets where when we project the cells onto it, they will become T-shapes or L-shapes or the like. And these we have to fill out with empty cells. Like if you would check back on the original grid, you would see that this empty cell here actually overlaps with part of the stitching geometry. So the approach here is just to fill those out with empty cells. And then we repeat that, but for the next coarser level. And you can see that we again choose gridlets of size 2x2. We choose the same size of gridlets on the next level, and with a coarser imaginary macro cell grid. And that eventually gives us our optimized data structure, which is the combined stitching geometry and gridlets. So in here you can see this in action. This is the molecular cloud data set from before with volumetric path tracing and a nice animation. These are the voxels in white and blue with this checker pattern, and in between the red stripes are the stitching geometry, so you can see most of the data is voxels. And this color coding here shows the gridlets of the various level. Each different color means different gridlet. So, and given that data, we still have to render it, of course, and the idea here is that you could basically take any off-the-shelf unstructured element renderer and extend it to be able to render gridlets. So, what a typical unstructured element renderer would lack here is support for a gridlet data structure whose data is vertex-centric, that supports trilinear interpolation, and then you also need some special handling for empty cells in case you have gridlets that are T or L shapes. So we actually implemented this ourselves in a prototypical renderer, and the data structure that we used for the gridlets is this compact representation here, where all the scalars are stored in a large array. And our gridlet stores an offset into that array, and it also stores a lower corner, and then it stores the refinement level, and from the refinement level we can compute the size of the gridlet in cell ON world space. So this is a very compact representation compared to a representation for a general hexahedra. There are different ways to render this kind of data, and what we chose to do is write an optics path tracer. Our optics path tracer supports Woodcock tracking. And the actual lighting model isn't that important here. What's more important is how we choose to perform sample reconstruction, and for that we chose the method by Wald and colleagues, who proposed to sample this kind of data using zero-length arrays. So what they do is they take every element from the data set and then build a BVH over those elements. And then they shoot rays into the data, and if the origin of those rays overlaps an element, then they know the point that this element is associated with is inside that element. This is part of our geometry here. We have stitching geometry here, and then we have gridlets there. And then what we do is we build separate BVHs. This is a BVH over all the gridlets. This is a BVH over all the unstructured elements. And then when we perform sample reconstruction during path tracing, We have our random walks that the path tracer performs, and we have to perform sample reconstruction, and then we take those small rays here and align the ray origin with the sample position that we're interested in. And here, what we detected is that we come out in an unstructured element in a hexahedron supposedly, and then we know that we sampled this element. So and if we happen to sample a gridlet, it is indicated here. What we have to do is we perform trilinear interpolation inside that gridlet. So there's special handling for this data type. Given that data structure, we performed a quantitative evaluation. And the first thing that we are interested in is the compression ratio that we can realize. For that, we first computed how much memory we would consume when actually every voxel was a hexahedron. And then we have our algorithm run over it and construct gridlets, and then we computed the difference in memory consumption between dataset with gridlets and dataset without gridlets. And what we observed is that the compression ratio is always on the order for datasets of approximately 1 to 8. So the next thing that we are interested in is peak memory consumption on a GPU. We measured this with an NVIDIA A6000 GPU and a workstation. And we compared against different reference methods. The first reference method we already talked about is the method by Wald and colleagues. But what we did is we actually plugged only hexahedra in here, but not gridlets or voxels. So we basically built a BBH over all the elements. And this is pretty much what software like, for example, Visit or ParaView would do when they render on the dual mesh. Then we used another reference paper by Wald and colleagues who compress the unstructured mesh data severely, so reference number 1 here. And then we use a non-dual mesh AMR renderer, the Hexabricks software, also by Wald and colleagues. And then we measured memory consumption using NVIDIA SMI. And we can see that we beat every unstructured element rendering method by a significant margin. In particular, the bigger the data sets are, we can see that we perform much better in memory. And what we also observe is that we beat Hexabricks, which is a non-dual mesh AMR rendering tool, in peak memory consumption. Not always, but at the very least for the bigger data sets. So, and finally, we report frame rates for that same configuration with an NVIDIA A6000 workstation and computing full GI. The absolute numbers aren't so important here because it's a very particular rendering method that we chose, and other rendering methods might perform differently. But what we see again is that we're ballpark similar to Hexabricks, which is dedicated AMR, and that we again always beat all the other unstructured element renderers, given that they are able to render our data. And that brings me to the conclusion of my talk. I presented a very efficient AMR data structure, namely rendering on the dual mesh, but in an optimized way, other than what currently visualization systems such as, for example, Visit do, to convert all the data to generally unstructured elements without any assumptions about the structure of the actual data, but instead we identify all the voxels in the data, collect them into what we call gridlets, and basically the rendering method stays the same. So if you take any off-the-shelf unstructured element renderer and extend it with a gridlet data type, such as ours, then it will also be able to render this kind of large-scale AMR data that we target in our publication. We can show that we beat any such unstructured renderer, but we also showed that we're highly competitive against optimized non-dual mesh AMR renderers, both in terms of memory consumption, where we were actually able to beat them, and in terms of frame rate, where we are able to render with performance in the same ballpark as those renderers do. Finally, here are the references we compared against Wald's memory-efficient encoding for ray tracing large unstructured data, which is a compressed unstructured element renderer, and we compared against Hexabricks, which was a publication at IEEE Vis in 2022. Finally, I would like to thank my funding agency and other people who helped us realize this paper. And that concludes my talk. Thank you very much.